So we've seen before that if you have eigenvectors for different eigenvalues, then they're going to be linearly independent. And in fact, in an inner product space, they're actually going to be orthogonal. So the same thing is true for generalized eigenvectors, at least for the independent part. So if let's take a bunch of distinct eigenvalues, so these are not necessarily all the eigenvalues of t, but it's just some group of distinct eigenvalues, then the corresponding generalized eigenvectors v1 through vn are going to be, oops, that should be vm, are going to be independent. Okay, so for the proof of this one, let's start by considering v1, and we're going to choose a k such that t minus lambda 1 I raised to the k applied to v1 is not 0. But if we do it one more time, then it is 0. So, in other words, we know that if you apply t minus lambda 1 I to v1 enough times, it's going to get dead. And so k is going to be the largest number of iterations that you can do before killing it. So one more will kill it. Okay. So then let's see. So then if we take w to be that thing we have at the last step, so after k applications, this guy, w is going to get killed if you apply it once more. So w is an honest, real and true lambda 1 eigenvector. Yeah? So if we apply t minus lambda I to w, and so now here, notice I'm intentionally not putting a subscript on this one. So this is not lambda 1 necessarily, it's just some scalar. And so, in fact, yeah, here, let's just make a little song and dance about this. Let's give this guy his own line so we can see how they're right next to each other. And so then this is tw minus lambda w. And now since w is a lambda 1 eigenvector, the first one becomes lambda 1 w. And then I can factor out the w. So we have this guy, right? And so this expression is going to be equal to 0 if and only if lambda equals lambda 1. So if lambda equals lambda 1, then we get 0 exactly as we should by this equation. However, if lambda is not equal to lambda 1, then this is not 0, and this is not 0, because we said so back here. Okay. And then if you keep on doing this, so if you apply the operator multiple times, then t minus your generic lambda raised to the whatever, say n applied to w is lambda 1 minus lambda to the n w. And that's, okay, you know what, just for full fluidity, we'll say, well, actually here, let's not take k, let's take l for any integer l. Okay, turns out we're only going to need it for l equal to n, but you can see that it's true, so hey, why not? All right, so now we're going to apply the operator. By the way, maybe you've seen in a differential equations class something called the method of annihilators, and maybe something seems familiar to you when you're looking at this, so just throwing that out there. If you haven't seen the method of annihilators, don't worry about it. So we're going to take t minus lambda 1 I raised to the k, and then for all the others we're going to raise it to the power n. So we've got t minus lambda 2 I raised to the n, and t minus lambda m I raised to the power n. So all those other ones are raised to the power equal to the dimension of the vector space. Okay, and so we're going to apply this operator to the dependence relation. 0 equals a1 v1 plus a2 v2 plus an vn, right? So we're trying to show that these things are linearly independent. So we assume that we have this type of an equation, and so then we're going to have 0 equals, and then we're going to take this whole big hairy mess and we're going to apply it to a1 v1 to an vn. And now what do we have here? Well, notice that we can reorder these. So all of these guys commute with each other. And that was some theorem back in chapter 5. If you have polynomials in T, they commute with other polynomials in T. Okay, and so we can look at what happens specifically to the components of this. So let's see. So this guy is going to kill off. Oh, hold on a sec. I just realized I have to fix my. I just typoed. These have to be m's, not n's. Okay. So this one is going to kill off this guy, and this one is going to kill off this one here, which maybe I'll just write in for grins. There we go. And so on and so forth. So all of these guys are going to get dead when I apply this operator, and I can do that just by, like I said, these commute. So I can shuffle this one so it's out here in front, and so it'll meet up with this guy and kill it. And I can shuffle this one and put it up in front when applying it to this guy, although he doesn't die, right? So since that's the one that only goes to the k, what we get there is a1 and then the rest of the business. Okay, and then all the others are dead by that argument I said. Okay, and so now for each of these, what we have is by our little earlier calculation up here, this is a1 lambda minus lambda 2 to the n, lambda minus lambda m to the n, v1. And so now in particular, if this is v1, so these guys are all lambda 1s. There we go. Bam, bam, bam. Okay. And now since we're assuming that these eigenvalues are different, then we know that none of these terms are going to be equal to 0. So then the only way that this whole expression can equal 0, since v1 as a generalized eigenvector is forbidden from being 0, that implies that a1 has to be equal to 0. But then you can do the entire same song and dance for all of the other components. So by same argument or by similar argument or whatever, you can come up with your own creative acronym for what BSA stands for. It'll work for all the others.